Good morning, everyone. This is Sachin Fiske from Electrical Engineering Department, SND College of Engineering and Research Center. In the previous lecture, we discussed about the root locus and properties of root locus. So let us take one overview of this root locus. Basically, the characteristics of the transient response of a closed loop system are related to location of the closed loop poles. If the system has a variable loop gain, then the location of the closed loop poles depends on the value of the loop gain chosen. And it is important that the designer know how the closed loop poles move in S-plane as the loop gain is varied. Even the introduced a graphical method for finding the roots of the characteristics equation known as root locus method. The root locus is used to study the location of the poles of a closed loop transfer function of a given linear system as a function of its parameters. Usually, a loop gain given its open loop transfer function. Here, the root depending on a particular value of the system parameter can then be located on the root locus or the value of the parameter for a desired root location and can be determined from the locus. It is powerful technique as an approximate root locus sketch can be made quickly and the designer can visualize the effect of varying the system parameter on root location or vice versa. It is applicable for single loop as well as multiple loop system. To understand the concept underlying the root locus technique, consider the second order system as discussed in the previous lecture. Now, moving towards the overview of root locus. Let us see in the design and analysis of control system, it is often required to investigate the sensitivity due to the variation of the parameter in such a system or controller. The root locus method plots are the trajectories of the roots of the characteristics equation when certain parameter in the system varies. Given the pole zero configuration, the construction of the complete root locus diagram requires search for the SI point in the S-plane that satisfies the equation. The determination of the value of k, that is either on root loci 0 is less than or equal to k is less than 1, or the on complementary root loci, that is minus infinity to 0, means the value of k is lies in between minus infinity to 0. Expanding on the bullets can develop the rules to aid in plotting the root loci. Now, the construction of root loci. Number 1, k is equals to 0 point. That is, on complete root loci corresponding to the poles of g of s into h of s, as g of s is the gain of the system and h of s is the feedback of the system. Secondly, k is equals to plus infinity to minus infinity. That means the value of k should be lies in between minus infinity to plus infinity point, and on complete root loci corresponds to the value of zeros of g of s is to h of s. Next point, the number of branches on the complete root loci. So in that there are three various branches. First one is the branch. So locus of one root when k takes the value in between minus infinity to plus infinity. The numbers of branches is equals to the maximum numbers, that is mn, and its example let us consider s into s plus 2 into s plus 3 plus k into s plus 1 is equals to 0. Let us consider this example in the mathematical or control system form as, or it should be noted as the transfer function of the system. Let us take s plus 1 upon s into s plus 2 s plus 3 is equals to minus 1 upon k, or it should be noted as k is equals to minus in numerator s into s plus 2 s plus 3 upon s plus 1, where this k is equals to 0, which tends to s is equals to 0, s is equals to minus 2, and s is equals to minus 3. Also, k is equals to infinity, then the value of s will be minus 1, infinity, and second also infinity. And small n is equals to 3, then m is equals to 1. It shows tends to number of branches is equals to maximum, and n is equals to 3. Symmetrically of complete root loci, this symmetrical about the real axis or real coefficient. Also symmetrical with respect to the axis of symmetry of the poles and zeros of g of s into h of s. The next point is asymptotes of the complete root loci, that is the behavior at s is equals to infinity. As s tends to infinity in the above equation, the root loci for k is greater than or equals to 0 are asymptotic to straight line with the angle of theta k is equals to in numerator 2k plus 1 into 5 upon n minus m, where this k is equals to 0, 1, 2, and so on up to the mod of n minus m minus 1. And the complementary root loci, that is k is less than or equals to 0, the angle of the asymptotes are theta k is equals to 2k pi upon n minus m, where the value of k should be equals to 0, 1, 2 up to mod of n minus m minus 1, and thus there are n minus m asymptotes for each type of the loci. Then intersection of the asymptotes. So the intersection of two mod of n minus f asymptote of the complete root loci lies on the real axis of the s plane, and it is given by, just wait, sigma is equals to b1 minus a1 upon n minus m is equals to summation of j, that is the poles of g of s h of s minus summation of I, that is zeros of g of s into h of s, means the summation of poles minus summation of zeros upon n minus m, which is equals to, here b1 and a1 are the coefficient of growth of s, and it should be noted that these poles and zeros are either real or complex conjugate pair. The imaginary part will be cancelled, and here the root loci on the real axis is given as for k is greater than or equals to 0 on a given section of a real axis. This root locus is found if the total number of real poles and zeros of g of s and h of s to the right of the section is odd. For k is less than or equals to 0 on a given section of a real axis, a complementary root locus is found if the total number of real poles and zeros of g of s into h of s to the right of the section is even. Note here the complex poles and zeros of g of s into h of s does not affect the existence properties of a root locus and complementary root locus on the real axis. Now, the angle of departure from poles and angle of arrival at zeros. This angle basically describes the behavior of the root loci near a pole or zeros. And to find this angle, choose S or close to poles or zero. And how to use this? The angle of G1 of S1 into H1 of S1 is equals to summation of I equals to 1 to m at an angle S1 plus Zi minus summation of j equals to 1 to n at an angle of Si plus Pj, and that is equals to 2l phi, where k is less than or equals to 0. That is the complementary root locus. The intersection of this root locus with the imaginary axis, the points where the complete root loci intersect with an imaginary axis, and corresponding value of k may be determined using the roots Hurwitz table and solving the auxiliary equation. Here, the break-in and break-away point, that is saddle points, are given. So, to correspond to multiple order roots of the C, these points on the root loci correspond or to more root meeting or departing on the locus. Means branches enter is equals to branches leave. These breakaway points may not necessarily be on a real axis, and to find the breakaway point, use DDS of g of s into h of s, means the derivative of g of s of h of s is equals to 0, which should also satisfy. Therefore, 1 plus k into g of s h of s is equals to also 0, or we should use derivative of k, that is DDS of k is equals to 0. We should notate that all the real solution of DDS of g of s h of s is equals to 0 are the saddle point on the complete root loci, that is value of k should lies in between minus infinity to plus infinity, and the complex conjugate solutions are the breakaway point only if then satisfies the both equation. The value of k corresponding to saddle point is obtained by using k is equals to minus 1 upon g of s h of s. Thank you.